Work example 5.16, practice problem A. The second part of that asks what the molecular formula is if the molar mass is 90 grams per mole. So that means whatever this molecule is, whatever the elements are that make up this substance from the periodic table, when I take the masses from those elements and add them together, I get 90. So if I had one molecule, it would be 90 AMUs. If I had a mole of molecules, it's going to be 90 grams. Right? So when I add the mass on the periodic table, I can express it with either of those units, depending on whether I'm talking about one individual particle of a molecule or a huge number of those molecules all together in a sample. So the other information given here is that you have 53.3% carbon by mass. You have 11.2% hydrogen by mass, and you have 35.5% oxygen. So does this mean, this given information here, does it mean that I have more oxygen atoms than I have hydrogen atoms in my sample? If it's roughly 36% oxygen and only 11% hydrogen, does that mean I have more oxygens in the molecule? Not necessarily, because this is by mass. It's not by number. It means that 35.5% of the overall mass of the molecule is oxygen. And since the individual oxygen atoms are much heavier, on average 16 AMUs compared to 1 AMU for each individual hydrogen atom, I might still have more hydrogens than oxygens, because each oxygen is so heavy, it contributes more to the overall mass than a bunch of like 8 or 9 or 10 hydrogens would. So the way to determine this would be to say, well, if the overall mass is 90, and I know 53.3% of that is carbon, then I would say, well, if I have this molecule, per molecule, I have 90 total AMUs. So 0.533%. Actually, let's just do it this way. So I've got 53.3% means per 100. So a percent means I've got that many grams of carbon per 100 grams total. So that's a relationship. A percent, if it's given to you, is always a relationship. A percentage is the amount of a part of a substance divided by the total amount. So if it's a mass percent, that means I've got 53.3 grams of this substance per every 100 total grams of the molecule. And this is also a relationship. That relationship is I've got 90 grams total of the molecule per 1 mole of molecules. If I had a mole of molecules, it would be 90 grams. So if I cancel the grams of molecules here, and I plug things into my calculator. That was given. That's the molar mass. So that molar mass is the number of grams of the substance per mole of the substance. So that means that 47, well, I just round up to 48 because I've got two sig figs here. 48 grams of carbon per mole, or per molecule, per mole of molecules. .48 grams of that 90 total is the carbon. Yeah, so it didn't have a decimal there, but it should have. I mean, you're never going to be working usually with only one sig fig. Plus that 90, that would be measured experimentally, so you'd have to be using a terrible device to measure with only one sig fig. So you should have at least two. I'm not sure why the book doesn't do that, but it should. So then I'd do the same thing for the other atoms. So I would do 11.2 grams of hydrogen for every 100 total grams, and I multiply that by the 90 grams per mole. And so that gives me 10 grams of hydrogen for every mole. And then I do the same thing for the oxygen, 35.5 grams of oxygen for every 100 total grams, times 90 grams per mole. So again, the grams here of the molecule are canceling. So I know that I have 35.5 divided by 100 times 90 gives me 32 grams of oxygen per mole. So it's asking me to determine the formula for this substance. The formula for a substance, if the substance involves carbon, hydrogen, and oxygen, the formula is how many carbons, how many hydrogens, and how many oxygens are there in each unit of this substance or in each molecule, right? That's what the formula is. And so I use the percentages to determine how many grams of carbon, how many grams of hydrogen, how many grams of oxygen. And then if I want to figure out the number of carbons, number of hydrogens, and number of oxygens, I just need to figure out how many carbons do I need to get 48 grams. How many hydrogens do I need to get 10 grams? How many oxygens do I need to get 32 grams? Right, so if I have 48 grams of carbon, and each carbon has a mass of 12 grams, so how many carbons do I have? Right, so I could set that up as a conversion, or if you can't do that in your head. So if I want to know how many carbon atoms there are in 48 grams, well, each carbon is 12 grams of carbon per mole. So that's going to give me 4 moles. If I do the same thing for the hydrogen, how many hydrogen atoms or moles of hydrogen do I have in 10 grams of hydrogen? Well, each hydrogen on average is about 1 AMU, so 1 gram per mole. So that's going to give me 10 moles of hydrogen. And if I do the same exact thing for the oxygen, 32 grams of oxygen divided by 16 grams per mole gives me 2 moles of oxygen. Since a mole is just a number of things, if I know how many moles of carbon I have in a mole of molecules, and I know how many moles or numbers of hydrogens I have in a molecule, and how many numbers of oxygens I have in a molecule, these become the ratios in the formula. So I know I've got 4 carbons for every 10 hydrogens for every 2 oxygens, so that's the formula.